to have a better understanding of these real quantum materials by doing the quantum simulation. However, I want to emphasize being able to like prepare the quantum states or simulate them on this programmable quantum simulator or like a computer is not the whole story. Because in order for us to have a better understanding of this material, we should be able to like read out the quantum properties from these machines. However, I want to emphasize this readout of the quantum properties is not like a trivial task in many scenarios. So first challenge is due to the high dimensionality. So quantum objects, the full classical description of quantum objects is this density matrices, which is a D by D Hermitian matrix, where the D is a Hilbert space dimension. And by naively counting the number of parameters inside its density matrices, one may suspect we need exponentially like many copies of the quantum states in order to fully characterize these states. And indeed, that's the case and has been proven. So to just give like a sense how hard this is, so the state-of-the-art full quantum state tomography on like 10 or 14 qubits will involve over 1 million measurement settings and weeks to perform. And sometimes we don't want to do the full quantum state tomography, but we would rather want to learn the properties of the quantum states. For example, we want to measure many observables, such as the energy of some states on this Hamiltonian. And practically, this Hamiltonian will involve like many terms. Even though it's polynomial, practically it will take like a really long time. And third is due to the limited controllability. So that is more an issue in these analog quantum simulations. So these analog quantum simulators, they are special machines that designed for solving like a particular quantum simulation, like Fermi-Hubbard model, like quantum spin liquids. However, it has a fewer tuning knobs. So like doing verification of the quantum property is not like a trivial task. So it's desirable to have a method such that can serve as an efficient quantum and classical interface, such that probably one can like measure first and store this classical information and then maybe ask many questions of its quantum property later. So the aim is to learn like many properties of this quantum system on these large-scale quantum computers or simulators efficiently by designing the proper experiments. And of course, there are like many ways of doing this. Could be like using statistical method or some machine learning method mentioned by David and Una yesterday. But today I'm going to talk about one particular method called classical shadow or randomized measurement I'm really excited about, which proposed by Huangku and Praskill like 4 years ago. So there are like two properties I really like about this method. The first one is it has approval efficiency. So one can show that using this data set, one can predict many properties like linear property, nonlinear property simultaneously. And secondly, it doesn't require precise control because it involves like a random unitary evolution. So this will be like very useful in these analog quantum devices. But for this talk, I'll mainly focus on like a quantum computer. And if you're interested in the application in analog simulation, I'm happy to chat afterwards. So let me give like a very high overview of these classical shadows. So the classical shadow or randomized measurements usually involves like two steps: the random unitary evolution and then the computational basis measurements. So each time in experiments, we prepare this underlying like quantum system, which we don't know, and we choose a random unitary like a random unitary evolution from an ensemble we designed to evolve these quantum states. So after evolution, the state will be mapped to these like quenched states. And then we perform the computational basis measurement to measure these states. And after the measurement, the state will collapse to a B string, for example, 0101. We use the cat B to denote these product states. And crucially, on a classical computer, the last step, we calculate this back evolution of the B string state into the original basis. And this sigma hat is what now called a classical shadow of the quantum states. So equivalently, we can think using the Heisenberg picture, what we are doing is we're directly measuring these quantum states in some random directions. And each time when we perform this random projection, the state will collapse to this classical shadow data. And then we basically iterate this many times in the experiments. Each time we choose a different unitary to do the quench dynamics and then measure. After like many measurements, the data set we're going to have is this classical shadow data set. And each of the data, the classical shadow, is associated with a probability that has two contributions. So the first contribution is from the quantum mechanics Born rule, depending on the underlying quantum states. And the second contribution is this PU, which ultimately will depend on the unitary ensemble we designed. So it could be like a random Pauli measurements or like the shadow circuits. So in classical shadow, the measurement channel is a key concept in predicting many properties. So what is that? If we take an ensemble average of all these classical shadow data I showed you before, one can show this will be related to the underlying quantum state rho by this linear map M. So let's just call it this measurement channel. It's a linear map. And suppose this linear map, we can figure it out and it's invertible, then we can use that to predict many properties of these underlying quantum states. For example, we can predict many linear properties. So if we're interested in this trace rho O, we can replace the rho by M inverse acting on each of the randomized measurement, the classical shadow data. And this will basically converge to the this true linear property. And moreover, we can use the same data set to predict the nonlinear properties, such as we're interested in this trace rho squared O. We can basically replace each of the rho by M inverse acting on independent collection of the classical shadows. So without further ado, let me show you like two famous classical shadow example in the original paper. One is the random Pauli measurements, where the unitary ensemble is particularly simple, just need a single qubit random rotation. And the other is random Clifford measurements. One use a global rotation in this quantity dynamics. So for the first scenario, the measurement channel is a tensor product of this affine transformation. It's very simple. But then I want to emphasize, if we are using this scheme to predict like M Pauli observable, like P1, P2 up to PM, then the sample complexity scale as log M times 3 to the K, where K is the maximum locality of this Pauli observable. Basically, how many non-trivial Pauli operator in this Pauli string. So suppose in this set, all the Pauli are like local, where the K is independent of system size, then this scheme is very good for predicting local observables. And also it's experimentally easy because it only requires single qubit rotations. And for the second scenario, one can show if we are going to use that to predict this linear property O1, O2 up to OM, then the sample complexity scale as log M times trace OI squared. And suppose this observable OI is some low rank observable like a fidelity or a projector, then the trace OI squared is a constant. It doesn't scale with system size. So it can actually achieve a constant prediction for this fidelity prediction. So it's really nice. However, experimentally, it will be challenging because it will need at least a linear depth circuits to implement that. So these two schemes are basically can be viewed as extreme limits in this spectrum. So in the random Pauli measurements, this unitary ensemble doesn't create any entanglement. And then in these random Clifford measurements, this unitary ensemble creates a lot of entanglement. So it's really natural to ask, is there any scheme that can extrapolate these two limits? If that would be really nice. So that's basically one of our main focus. Like since 3 years ago, we proposed this locally scrambled unitary ensemble. So mathematically, it means that this unitary ensemble is invariant under the local basis transformation. So it's a sort of a fine-grained generalization of the Haar measure of the random unitary matrices. So despite this mathematical definition, I want to show you it's very easy to construct a local scrambled unitary ensemble, and it can be applied to a wide range of the unitary families. So first of all, suppose we have like a fixed signal gates, and I tour it by single qubit rotations. I basically apply the random single qubit gates each time. Then this will form a very small locally scrambled unitary ensemble. And then we can use this as a small gadget to basically form like an arbitrary structure, like a shallow circuits. And recently it has been applied to like this happy code holographic structure have like relation to ADS-CFT. And it can also be applied to a fixed unitary, maybe generated by some Hamiltonian dynamics and toured by single qubit gates. And if a unitary ensemble satisfies this local scrambling property, then the measurement channel is particularly very easy. So it can be shown that this measurement channel is diagonal in the poly basis, meaning that if you have insert a poly, it's going to rescale this poly. And then this eigenvalue is called the poly weights. And the physical meaning of these poly weights is basically the probability of measuring this poly operator directly if you are going to use this unitary ensemble. So think about the example of these random poly measurements, then this the eigenvalue, the poly weights, is going to be 1/3 to the k. And if this is diagonal, then the reconstruction is also particularly easy. We just to do the inverse of each of the eigenvalues in the of these poly weights. And using this physical idea, like a physical picture of the poly weights, people also theoretically show the logarithmic depth shadow circuits is also optimal for learning poly operators. So far it's been like anything I showed you is a unitary evolution. That's great, works out on theoretical level. But if one takes this to experimentalists, people will hesitate of doing experiments for two reasons. First, each additional layer of these shadow circuits will introduce additional noise. So how do we make it noise robust? So that's one of the questions. And then if we can make it noise robust, usually it will involve some error mitigation technique. And any like error mitigation will have the so-called variance bias trade-off, meaning that I correct my bias, but I have enhanced the sample complexity. So does it still like worth doing a shadow circuit shadow compared to random poly measurements in reality? That's also unknown. So basically, that's our like new work. We try to address this question, make it noise robust. So our setup is still we assume this local scrambling property of the unitary ensemble. The first layer and last layer are these like single qubit random rotation gates, and what is in the middle can be shallow circuits or some like a fixed unitary evolution, some fixed channel. It doesn't really matter. And what we can show is that if we assume the first layer of the single qubit random rotation gate is noiseless, then the measurement channel is still diagonal in the poly basis. So I think this is a valid assumption because in reality, at least in superconducting qubits, the single qubit gate has a significant smaller error rates compared to the measurement error and 2-qubit error. But then this time, these poly weights will be generalized to these noisy poly weights. It becomes a cross correlation between the ideal and the noisy value. And we show that if we know what are the noisy poly weights associated with each of the poly operator, we can basically use that in the post-processing to achieve this unbiased prediction. So how do we learn that? We proposed this direct calibration algorithm. So first we prepare the high fidelity 0 states, and we do this shallow circuit shadow. It will have noise. It will have noise. But then we perform the computational basis measurement. We collect these measurement results. And on a classical computer, we calculate this one-time estimator for the noisy shadow weights. And this UI is, I want to emphasize, that's the ideal like unitary evolution we are going to do. And then the noise basically will bias the probability distribution of observing each of the bit string. And we show that this one-time estimator will converge to these noisy poly weights, the cross correlation. And we also provide some theoretical guarantee of this direct calibration algorithm. Basically means that for any like epsilon error, a number of these samples in the calibration procedure is enough to guarantee the following prediction for any k local observable to achieve this epsilon times 2 to the k like precision with high probability. So this direct calibration algorithm can be applied to any arbitrary like structures. However, if we are going to use a shallow circuit, the circuit actually have a structure. And if we are utilizing the structure of the circuit, we can achieve a more like a better sample complexity in the calibration. So the key idea is that we utilize the circuit structure and then we combine it with some like heuristic Bayesian learning technique. So first of all, in reality, we are going to use 2 signal gates to perform this shadow circuit classical shadow. So following the idea of the randomized compilation work, we can basically show a stochastic noise model can be used in the data post-processing to effectively capture any like time-independent noise that happen in the physical circuits. So that is great. However, there are still like many Pauli generators in this noise model. So then we rely on another assumption, such as the on-site and nearest neighbor QB error are like more happen more often. So we will basically utilize this sparse Pauli-Limbaugh noise model with some unknown noise parameter lambda k. And suppose we know this noise parameter, then we can basically plug that into the definition and calculate the noisy Pauli weights and achieve unbiased prediction. However, there are 4 to the n different Pauli weights. So for each of the Pauli operator has an eigenvalue. How do we calculate that? Luckily, we can encode all these 4 to the n Pauli weights with some polynomial time and memory. Essentially, the idea is to utilizing the tensor network representation. So it can be shown that all these 4 to the n Pauli weights can be arranged into these synthetic quantum states where each of the like a physical lag has bound dimensional 4, meaning x, y, z identity, and the intra-bound dimension is polynomial in the system size. So now we have the algorithm and the noise model. Then we can basically use the Bayesian inference to learn the noise parameters. I will briefly show you. So we have this like prior distribution of the noise parameter lambda k. Well, we prepare the 0 states as benchmarking states, perform the classic shuttle, and then we can use this practical data to form a likelihood function to basically update our knowledge on the prior distribution to form this posterior. And then from that, we can read out the most likely noise parameters, and then we can use that for prediction. So in the paper, we also showed this, numerically, we showed it will have a better calibration sample complexity compared to this direct calibration algorithm. So far that's the theory, and we want to test it with the most real noise model, which is real devices. So we perform the experiments with the IBM machine. The first data I want to show you is the 18 qubits plus states and the cluster states, which are simple states. And the reason to do that is we want to have a direct estimation of many observables, such as fidelity, stabilizer, etc. Such that we know that we are doing unbiased prediction. So here, different color means that different circuit depths. So d equal to 0 is random Pauli measurements. D equals to 1, we use 2 layers of CNOT gates. D equals to 2, we use 4 layers of CNOT gates. And then the shaded bar is unerror mitigated vanilla shadow. The solid bar are prediction given by the robust shadow. And here is a prediction on the fidelity. So here first we see without any error mitigation, if we increase the circuit depth, the fidelity prediction will constantly drop. And the reason is because we are introducing more noise in this readout procedure, and we didn't take care of that. So it doesn't, is not because the state has a lower fidelity. However, if we do this robust shadow prediction, we see that all this fidelity will consistent with the direct estimation of the fidelity. And in the paper, we have more observables such as stabilizer expectation value, entanglement entropy using the same data set. And also, I want to show this only takes 10 minutes of the QPU time to collect the data to predict many properties. So 10 minutes probably doesn't mean anything, but still really good practically. The other question is whether we want to do shadow in practice. So what's the advantage? The advantage is that we can reduce the sample complexity. For example, if we are interested in some fidelity or low rank observable, so here is a plot of the standard deviation or the sample complexity against the circuit depth. So this is bootstrapped from experimental data. We see that with the same amount of data, if we increase the circuit depth, the sample complexity, the reconstruction error is basically decreasing. So that's the advantage of using the shadow in practice. And with a larger system size, the separation will be more apparent. And of course, we're also interested in Pauli observable. So these different dots are bootstrapped, reconstruction error from the data. And we show if we are using random Pauli measurements, beautiful curve 3 to the k predicted by the theory. And these two red and orange are the shadow with different circuit depths. we see practically it performs better than 2.28 to the k, which is a theoretical upper bound. And moreover, I want to emphasize all these dots are bootstrapped results from the experimental data, and these solid curves are actually calculating using our theory, and we see that it matches really well in terms of the sample complexity. So yeah, in the paper we also talk about this variance bias trade-off, meaning that having noise will basically shrink the circuit depth, but increasing the sample complexity. So the last experimental data I want to show is this a more interesting state called AKLT resource state. It's basically a constant circuit depth to prepare AKLT states proposed by Steve Girvan and his collaborators. So what we did is that we prepare the states, we predict more than 300 different entanglement entropy regimes between arbitrary two pairs using the same data set. So on the left, we have a theoretical prediction of this arbitrary entanglement. And then on the right, we have this experimental prediction. So we see that it really achieves the efficient prediction of many observables. I'll use the last 2 minutes to briefly talk about the future application we're thinking about. One of the application is spectroscopy. So understanding this energy landscape of the a molecule or material is kind of important. And we want to predict, for example, the lower energy spectrum of some molecules, for example. So on the really near term, there are a lot of attention on these variational quantum eigensolvers, use less quantum resource. However, on the in the long run, people want to do this quantum phase estimation. But we are trying to think about whether there are some middle region we can use measurement data-driven method to achieve this learning of the lower energy spectrum. So without telling you too much details, the algorithm, the circuit will look like this. So we prepare some simple initial states, and then suppose we want to learn the energy spectrum, lower energy spectrum of H. We use that to do basically quench dynamics. In practice, we'll use totalization, and then we touch these shadow circuits in the measurement result in this measurement phase. And then we can use that to predict many low-rank observables, this overlap. And from that, we combine it with some data analysis technique called dynamical mode decomposition and achieve this prediction of the lower energy spectrum. So here are some results. So first of all, we can show at least for ground state energy, we have understanding this method will have a exponential convergence above some noise level determined by the measurement error. And also I want to emphasize in this method, it doesn't rely on any heuristic classical optimization tool. So it's really nice. And it's a measurement data-driven method. And the last direction we're thinking about is the de-randomized shadow algorithm. So in some scenario, we don't care about predicting arbitrary properties. Maybe you are interested in a set of Pauli observables, which is a subroutine for many quantum algorithms. And if that's the case, we can basically do important sampling to measure to basically de-randomize circuits that can predict arbitrary Pauli to basically focus on this specific set of Pauli observable we are interested in. It also has some relation to the graph coloring and the overlap group measurements, which are mentioned by David 2 days ago. So heuristically, we benchmark these de-randomized shadows on a bunch of small molecules with a lot of different classical other methods, and we observe the state-of-the-art reconstruction using the same amount of data. So with that, I'll conclude my talk. So I guess the one take-home message is that we perform the robust shadow protocol, and then we show that it's actually robust in the for the real devices. And then there are 2 related papers. One is Jens Eisner's group. They talk about some special case one can actually use the these randomized benchmarking results to do the robust prediction. And then there's another interesting paper from David, Jonas, Robert on logarithmic depth circuits can actually mimic the linear depth circuits such that one can basically use this pseudo random to predict fidelity very efficiently. So with that, I will thank all my mentors and collaborators, and of course, thank you for your attention and getting up so early in the morning.